All right, so we just previously solved for the open circuit voltage, which is the Thevenin voltage, and the short circuit current, which is the Norton current. We threw them into our equivalents, and now what we're about to do is we're going to find the Thevenin/Norton resistance. So let me go back and take this circuit. This is the one that we're interested in analyzing. And we need to follow the steps necessary to find the Thevenin/Norton resistance. So let's go ahead and do that. So the first step there is we need to short all voltage sources and open all current sources. Well, we don't have any current sources, so we're just going to short our voltage source, and then we want to find the equivalent resistance between the load terminals. Okay, so let's go ahead and short. Let me get rid of this and this. Oh, not that, just this. And we are going to short our voltage source. So we got a short here now, and we want to determine what is the equivalent resistance that I see looking into this load terminal, okay? And I define this as basically if I were to send a test current, I can call it I test, into my circuit, what resistance would it have to see before it makes it back to this other terminal, okay? And so first, obviously, it would see a 3K resistor, but then it sees a node where it sees 1K and 2K. Well, you can notice, and I hope you do by now, that the 1K and the 2K are in parallel. They share this ground node, and they also share this node pretty obviously. And so because they share two nodes, they have the same voltage across them. Those two are in parallel. And so the resistance, total resistance that I'm going to see if I'm this test current is I'm going to see 3K, and then I'm going to see in series with that 3K, I'm going to see a 1K in parallel with a 2K. So if I want to write my R Thevenin is equal to R Norton, that's going to be 3K plus whatever 1K in parallel with 2K is. It's going to be 1K times 2K over 1K plus 2K, or basically, what is that going to be? 2/3, so 7 ohms. Okay. That's just this, sorry. That's not the total. The total is 3K plus that. So let me write that this is 667 ohms. And so my total would be 3.667 kilo ohms. And now I can take that, and that is going to be my Thevenin resistance and my Norton resistance as well, okay? So I've got everything I need to plug my load back in, and I'm going to go ahead and put it right here, 1K, and I'll put it right here as well. And what did I expect from the first slide? I expect that my voltage in both cases should be 1.28 volts. If you don't remember, I'll go back real quick. 1.28 volts, and my current should be 1.28 milliamps as a result, because it's a 1K resistor. So let's go ahead and just make sure that that is the case. This one is pretty simple. It's just a voltage divider. I can say that my V load, in this case, I'll call it V load test, is equal to 6 volts. So V load test is basically this node voltage here. It's going to be 6 volts multiplied by 1K divided by 3.667K. And that should give me 1.28 volts. So let me throw it in my calculator. If it doesn't give me that, then I'm going to be very sad, because that means I wasted a lot of time doing this example wrong. not 6 volts times 1K over 3.667, but 4.667K, because I have to add them. And that's going to give me 6 divided by 4.667 gives me 1.28 volts, which is awesome. And that means that I would get 1.28 milliamps flowing through the resistor, which means that my Thevenin equivalent is correct. Okay, so that is a check. Let me go ahead and shrink this down a little bit so I can make some space here. And now I need to check my Norton one, my Norton equivalent. My Norton equivalent basically shows me that I have 1.63 milliamps flowing into a 1K in parallel with a 3.667K. So in order to determine the voltage, I just need to take 1K times 3.67K divided by 4.667K. That's my equivalent R multiplied by I. And I should get 1.28 volts. Let's try it out. So it's going to be 3.667 divided by 4.667 multiplied by 1.63, 1.28 volts. All right. So that is proof. And of course, if I have 1.28 volts here across a 1K, that's going to give me 1.28 milliamps flowing through the 1K. So that is proof that my Thevenin and Norton equivalents are correct. The values agree with what we got in the original circuit with no equivalent. That is just replacing all of this with a Thevenin and a Norton equivalent. We put the load back in and we determine our voltage and current to be the same in both cases, which means that these equivalents are correct. This is a very lengthy example. I know it's taken up 3 videos, but Thevenin and Norton problems are pretty challenging. I'll probably solve more examples, or at least one more example like this in another video in the future. Obviously, if you have any questions, feel free to ask. I know this is a pretty tough topic. It's just a lot of steps and a lot of solving circuits that goes into this. But in the next video, we're going to move on to one final little note on Thevenin and Norton, and then we will move on to the last topic of this module, which is called source transformation.